Hello, my name is Lorenzo Santilli, and we are team number 17, and the project we chose is Austere Field Light Attack Aircraft.
And I'm Dalton Vega. I'm a third year.
I'm William Bellflower. I'm a second year.
I'm Owen Patterson. I'm a second year.
Wani, I'm third year. Okay, so the ultimate goal of our project is to develop a light attack aircraft which can perform takeoff and landing in austere fields, provide close attack support at short notice, and to perform missions currently dealt by helicopters only. Then why is it important? Firstly, it will improve the United States' ability to counter enemies. Next, the close air support in time can be life-saving for the ground forces. Next, it can also decrease operation costs by finding the great balance between the conventional and cutting-edge technologies, and hence it must be a valuable new option to optimize air missions. Next. The stakeholders for this project are the US government, the US Armed Forces, private aerospace and defense companies, pilots, and the US citizen. Next.
As all stakeholders have needs and goals for their projects, we have plenty to go with ours. Some of the major ones, the aircraft needs to be able to take off from less than 4,000 foot runway, carrying up to 3,000 pounds of armament. It needs to be able to sustain wear and tear for 15,000 hours over 25 years. It must be equipped with oxygen for high altitude flying. Some of the more optional requirements are the ability to carry and launch rockets and missiles, as well as be able to drop bombs and have countermeasures in dogfighting or against other aerial attacks.
And so on to the concept of operation or ConOps for this aircraft. The aircraft starts off at a forward operating base with potentially a short or austere runway, and at which it is loaded with the proper munitions for the mission, and then it establishes communications with air traffic control or other other aircraft in the fleet. So it takes off using any kind of short field procedures as necessary, and then climbs to its cruising altitude where it navigates to the area of operations. At this area, there may be enemy forces or friendly ground forces as well, and the mission may require that the aircraft deploy munitions onto the target. And in that case, it may also need to evade return fire and then also loiter around the area for an extended period of time. It then climbs back to its cruising altitude, after which it navigates back to the base and lands using at an airport with potentially needing any short landing procedures. And the functional top-level requirements for this aircraft are the ability to carry all types of munitions currently in use for modern close air support vehicles. It has to carry two pilots who must be able to eject in all conditions, including being stationary position on the ground, also known as a 0-0 ejection seat. Must be able to fly in adverse weather and be controllable in the event of a control failure. For performance requirements, very important is that it must be able to take off in less than 4,000 feet for austere runways, and also land, and also have be able to take off and land at a density altitude up to 6,000 feet. These runways can be semi-prepared with grass or dirt, and they can have as much as a 50-foot obstacle for takeoff and landing. And a few other things, service ceiling must be at least 3,000 feet, and loader time must be at least 4 hours.
So some other concepts, vehicles that are currently used in this role. The A10 Thunderbolt is designed as a heavy attack and support aircraft, and it's meant for taking out targets like tanks, but isn't quite as effective at small, nimble targets that we see in modern battlefields. This aircraft is built around a 30-millimeter rotating cannon that fires depleted uranium rounds, which is an example of one of the expensive materials used in this vehicle that makes it difficult to maintain and has hurt its already long service life. Another concept vehicle that is seeking to enter service in light attack role is the F-35 Lightning II. This is designed as part of the Joint Strike Fighter program to fill a multitude of different roles in the U.S. Armed Forces. It's designed with excellent stealth capabilities. It has short takeoff and landing capabilities. But ultimately, it wasn't designed specifically for this role, so it is not as effective as it could be, especially due to those stealth capabilities that force all the weapons to be maintained inside the vehicle. It's also marred in political controversy due to some of the expense and the cost overruns and timeline overruns that have occurred with this project. And this is our final sketch design. The vehicle that we have created to fill this role, or one of the concepts we've come up with. This is using counter-rotating propellers, centrally mounted turboprop engine, and an H-tail is some of the important features in its survivability in this role. And yeah.
This is the functional decomposition diagram of the whole system. The 5 top categories are based on the CONOPS in time order, and the right 2 categories, the avionics and communications, of which must be performed at all times. Next. And this is the physical decomposition of the system, formulated from our functional decomposition just showed. The main system is made up of several subsystems, as you see on this slide. Here, focusing on the major goal and requirement of the aircraft, the landing gear is further decomposed into shimmy damper, struts, and wheels, so to emphasize the importance of its robustness in austere conditions. Next.
And so here is a morphological matrix that details all of the architecture options for this aircraft. For example, this matrix helps us lay out the options for propulsion, our wing planform, the gun location, stability, countermeasures, airfoil, and redundancy. And so the trade studies that we'll cover in the following slides will help us choose options for each of these and help us further refine our choices for this aircraft.
For interfaces, this is an N2 diagram that we made, and this basically describes the subsystems at a high level and how they communicate with each other. And these subsystems are basically like avionics and mechanical systems. So in the light blue boxes, these are the subsystems, and we have communication, navigation system, an accelerometer, electronic data systems, maneuverments from the pilot, and the payload and attack system. And the dark blue boxes basically describe the certain inputs and outputs. So on the right side, we have the inputs, and on the left side, we have the outputs. And example can be from the payload and attack system. The certain inputs we need are from the maneuverments of the pilot, and also from the electronic data systems when we know that the target is locked in, and also communication from the command station giving permission to attack. And this output, once the attack is made, it has to be reported back with the communication system. And we also have like electronic data systems that transmit this data as well. Next slide.
So with all these subsystems, we have different requirements for each subsystem. For example, the body frame, as mentioned before, must be able to last for 15,000 hours over 25 years, thus withstand substantial amounts of G-force. The engine must be able to withstand weather conditions ranging from extreme cold to extreme heat, varying density altitudes. After the engine subsystem, we have the hydraulic fuel subsystem, which has to be able to have enough oil reserve and gas for trips in excess of 900 nautical miles and still have reserves for at least 45 minutes of flight. The pneumatic and mechanical systems must have oxygen for flights above 15,000 feet up to 30,000. We have to have proper airflow in case of leaks. They also must have landing gear that is suited for a California bearing ratio of 5. Along with the last subsystem we have is the electrical subsystem, which we must have a reserve battery in case of loss of power so that no matter what, we can continue the flight and land safely. And that's sum up of the requirements necessary for our subsystem.
Okay, so 2 trade studies were conducted in order for us to narrow down some of our alternatives in these regions. The first one, the propulsion trade study here, following a Pew evaluation method. We looked at 3 alternatives with 1 datum point, piston engine being the datum point, and turbojet, turboprop, and turbofan being our 3 alternatives. And based on our analysis here, the trade study indicates that the turboprop is likely the best option. It has similar performance to the piston engine in most metrics. Its only minuses are in cost, maintenance costs there as well, but this can be made up, or likely will be able to be made up through efficiency increases and better reliability on the engine during its service life. Our second trade study was conducted for the control system here. This trade study indicates that the cable system is likely the best option, again following the Pew evaluation method. Both the electric and hydraulic systems present risk of damage and maintenance in the combat zone, and which is in this case a negative, but it is possible that a combination of hydraulic or electric and cable systems would be the best option, because both of those provide increased control authority over the vehicle, while the cable system would act as a backup should one of these more complex and powerful systems fail. Ultimately, this is the choice that we made for our vehicle, is to have a combination of both electric and cables in order to get the best of both systems.
And so here is the same morphological matrix that you saw earlier. Now we've decided of which option to choose for each category. So some of the major ones is, as said earlier, we chose a turboprop engine, and a total of 1 of those at the front of the aircraft. We have a straight wing planform, and we're going to store our payload externally using a hybrid control system. And our structure will be out of aluminum. We'll have some chaff and flare plus active jamming for countermeasures. And our control redundancy will have a backup mechanical system.
So ultimately, we defined a concept architecture here, as shown earlier. Here again, some of the important features here are the H-tail, which provides redundancy in case one elevator or rudder combo is damaged during combat. The vehicle still has control authority in order to return home. Another feature is a centrally mounted engine connected to the propeller via a drive shaft, and this allows for a single armor plate to protect both the pilots and the engine. We have twin screw counter-rotating propellers there to prevent torque roll on the aircraft, and a single cannon fires through the nose, fulfilling the armament requirements laid out in the project. Some of the benefits here, the conventional airframe layout makes production simpler, and this will allow us to meet the 2025 service entry date. The design choices maximize the survivability of the aircraft, protecting the most important and vulnerable components, obviously the pilots and the engine there. And with a large, powerful propeller, powerful turbine, and sturdy landing gear, this vehicle will fulfill the landing requirements set out by the project. And finally, with the centrally mounted cannon, it will be easy to fire accurately, and it will allow for more ammunition to be stored in the nose rather than wing-mounted configurations.